Continuing with the series, today I will be covering the Gauteng Province March 2023 paper. And our first question is asking us to solve for x with 5x cubed minus 20x being equal to 0. The first thing that we're going to do is take out our common factor. This, we're going to take out x. We already have our first solution, x being equal to 0. We have to solve for this now. I'm going to transpose the negative 20 to that side. Divide all the way by 5. Find the square root of x. X is going to be either negative or positive 2. That's our first solution. This question is a lot more different than the previous one. Usually if we had 0 on this side, we'd find x is equal to 0 and then this expression equal to 0. But because we have 6, we need to distribute this x across these brackets. So 10x multiplied by x is going to be 10x squared. X multiplied by 2 is going to be negative 2x is equal to 6. We're going to take this 6 and then take it to that side. From this stage, you can use the quadratic equation. You are allowed to use it. Where are these going to be negative 2? Our A is going to be 10, and our C is going to be negative 6. Our solutions are going to be this one is a lot more interesting because we have our x in the exponential regions, but another trick to this is that we also have sine and cos. So now our main objective is to bring down these exponents to the base status, but we also have extra information. We are told where x is a value between 0 and 90 degrees. So our answer has to be an angle within the first quadrant. The first thing that we're going to do, we want to make these bases alike. We know that 25 can also be written as 5 squared. So 5 squared multiplied by this 2 sine x minus 5 to the power of 4 plus x is equal to 0. 5 2 multiplied by 2 sine x is going to be 4 sine x minus 5, 4 plus x. The first thing that I did was to make these two bases alike. The reason behind that is that in exponentiated expressions such as this one and this one, if the bases are the same, then the exponents can be equated. So from this instance, we have 5 here, we have 5 here. This means that 4 sine x is equal to 4 plus x. If the bases of an exponential expression are equal, then the exponents are equal as well. That's why we have 4 sine x is equal to 4 plus x. We have a common factor being 4. We remove the 4 on both sides. We're left with sine x is equal to cos x. We're going to divide by cos x. Sine over cos is tan x. This side, cos over cos, we're going to be left with 1. But remember, we're still solving for x, so x is equal to 1. This is 45 degrees, which fits in this restriction. There are various ways we can solve this, but the simplest way that we can do it is letting 7 and the square root of x be k. We're going to substitute k in everywhere we see 7 and the square root of x. So it's going to be k plus 42 is equal to 343 over k. We don't want k as a denominator, so we're going to multiply it out. From here, we can use the quadratic equation. K is going to be 7 and 49. But remember, we're not solving for k, we're solving for x. So we're going to bring back 7 and the square root of x here. Divide by 7, both sides. The square root of x is equal to 1. We don't want the square root of x, we want x. Square both sides. Our x is equal to 1 on this side. This one, 7 and the square root of x is equal to 49. Divided by 7 on both sides. Our square root of 7, our square root of x is equal to 7. We don't want square root of x. We want x square both sides. X is equal to 49. Solving simultaneous equation. We need to solve for both x and y at the same time using two equations. The easiest way to go about this is to try and work around an easiest looking equation. So from this one at the top is the most easiest looking. So from this one, we're going to make x the subject of the formula. We'll transpose all 2y and 3 to that side. It's going to be negative 2y minus 3. This will be our first equation. And then this will be our second equation. Everywhere where we see x in the second equation, we're going to substitute this expression. We have y squared plus 6y plus 8 is equal to 0. If you want to use your quadratic formula, you are allowed to use it. But from here, you can also see that it's y plus 2 as well as y plus 4. Therefore, y plus 2 is equal to 0, or y plus 4 is equal to 0. And the solutions for y is negative 2 and negative 4. Now we're going to substitute y into the first equation to find our x's. X is equal to negative 2. Our first y is going to be negative 2 as well, minus 3. This is going to be positive 4 minus 3 is going to be positive 1. Other x is going to be negative 2 multiplied by negative 4 minus 3. This is going to be positive 8 minus 3 is going to be 5. Now, for the last question on this section, we have been given 3 equations, this, and this, and we're told we need to prove that 2 is equal to the product of each of x and f of x plus the product of each of x and g of x. From these 3 equations, there's only one equation that has 2, and it's this third one, 2, which is in the exponential region, to be a base. That's the first thing that we're going to do. How are we going to do that? Rewrite the equation to k to the power 2 over h of x is equal to 12. And one way to manipulate this is to look at 12. 12 can be written in a lot of different ways. The simplest way that can help us solve this entire thing is that we can write 12 as a product of 3 and 4. So k to the power 2 over each of x is equal to the product of 3 and 4. But we do know from our given equation that 3 is equal to k to the exponent f of x, and then 4 is equal to the k to the power g of x. So we can rewrite them in place of 3 and 4. So we have our k 2 over each of x is equal to k to the power f of x multiplied by k to the power g of x. If you go back to your exponential laws, you know that if we have a product of 2, if we're multiplying two exponential expressions that have the same basis, then we can add the exponent. So our k on this side, 2 over h of x, is equal to, they share the same base, so we can add the exponents plus g of x. And then another law is that if you have 2 exponential expressions that have the same base, then you're allowed to equate the exponents. So this side has a base of k, this side has a base of k. We can write down 2 over h of x exponentially equal to each other as g of x. So from here, we don't want each of x as a denominator, so we're going to multiply it out, h of x, so that we have our 2 being equal to h of x. Remember, h of x multiplied by f of x plus h of x multiplied by g of x. We have proven